You've probably heard that famous line from Einstein, mass tells space-time how to curve, and that curvature tells mass how to move. Sounds simple enough, right? But what exactly is doing the telling? What is the true source of all gravity? Well, that's the mystery we're going to unravel today.
So, what is it? What's the one thing in the universe that tells space-time how to bend, creating the force we call gravity? As we're about to find out, the answer is way more interesting and honestly a lot more elegant than you might think.
This right here is where Einstein started, his first draft of the equation, if you will. It sets up the relationship perfectly. On the left, you've got the geometry of space-time curvature. And on the right, well, you've got a placeholder, a big question mark, a measure of matter energy density. He knew the idea, but he needed the precise mathematical object. Our job is to figure out exactly what goes in that box.
Okay, so the most obvious first guess for what creates gravity is just stuff, the density of matter. How much mass is packed into a certain amount of space. It feels right, it's intuitive, but as we're about to see, in the world of relativity, the intuitive answer is rarely the whole story.
So, let's start with a simple thought experiment. Picture a box filled with particles. If you're just sitting there right next to the box, its density is super easy to figure out. You just count the particles, measure the volume, and do the division. Simple. We call this the rest number density. So far, so good. But what happens if you fly past that very same box at, say, 90% the speed of light? This is where things get weird. This is where relativity kicks in. To you, the moving observer, that box actually appears squished in the direction it's moving. This is a real physical effect called Lorentz contraction. Now, the number of particles inside is the same, but the volume you measure is smaller. And a smaller volume means, you guessed it, a higher density.
And this is a huge problem. We have two people looking at the exact same box of stuff, and they measure two totally different densities. So what does that mean? If gravity depends on density, is gravity subjective? Does it depend on how fast you're moving? No way. That can't be right. We need something fundamental, something that everyone agrees on, no matter how they're moving. So density alone is out.
To solve problems like this, physicists came up with more powerful mathematical tools. One of those is something called the number current 4 vector. Now, you don't need to get bogged down in the math, but the key idea is that it cleverly combines the density of particles, how many there are, with their flow or their current, where they're all headed. It's a big step in the right direction because it's an object that all observers can agree on. But it's still just talking about particles, not the full picture of what causes gravity. So if simple density fails us, what's the answer? Well, it turns out Einstein needed something completely new, a mathematical object that could hold all the information about not just how much stuff there is, but how it's moving, how it's flowing, and even how it's pushing and pulling on itself.
And here it is. Folks, meet the hero of our story, the stress-energy tensor. This is it. This is the complete, correct, and absolutely beautiful thing that goes on the right side of Einstein's equation. It's the full description of everything that can possibly source a gravitational field.
When you write it out, it looks like a 4x4 grid of numbers. I love to think of it as a cosmic recipe. Each one of these components is a different ingredient that tells space-time exactly how to curve. It's not just saying, hey, there's some stuff over here. It's saying, here's what the stuff is, here's where it's going, and here's how it's interacting with itself. It's the whole shebang.
So, let's break down this recipe. What are the ingredients? Well, first you have energy density. That's kind of like our old friend mass density, but on steroids. Then you have momentum density. That's all about where the stuff is going. You've also got energy flux, which is how that energy is flowing. And then you have the really wild ones, stress and pressure, which describe the internal forces pushing and pulling inside the stuff itself. Let's start with that top left corner, the T00 component. This is the king. This is energy density. It's basically E equals mc squared in action. It includes the energy locked up in mass, but also the energy of motion, of heat, of fields, everything. It's the main ingredient, the one that makes the most intuitive sense to us.
Now for the rest of that top row and first column. These terms are all about momentum and the flow of energy. And this is just so cool, because it means that it's not just the presence of energy that bends space-time, it's the movement of that energy. The flow of energy is itself a source of gravity. A massive spinning star literally drags space-time around with it. That's called frame dragging, and it's because of these very terms.
And now for the part that just blows my mind every time. The rest of the components in this grid describe stress and pressure. This means that the incredible, violent pressure at the core of a star, the very force pushing outwards that stops it from collapsing, is also a source of gravity, pulling it inward. Think about that for a second. Pure pressure, just a force, can bend the fabric of reality. That is just wild.
To get a feel for this, just push down on a table with your hand. The force you're spreading across the surface of your palm is a type of stress. Now imagine that on a cosmic scale. All the particles inside a star are slamming into each other, creating an insane amount of outward pressure. That collective push is a stress, and according to Einstein, that stress has gravitational weight.
So now we have it, our complete cosmic recipe, the stress-energy tensor. And the real magic of this thing is how universal it is. With this one mathematical toolkit, we can describe the source of gravity for literally anything and everything in the cosmos.
I mean, just look at how versatile it is. For stars and galaxies, we can model them as a perfect fluid with just density and pressure. For pure light, it behaves like a special kind of fluid, where the pressure is always 1/3 of the energy density. And even for empty space, the tensor can describe vacuum energy. You know, the mysterious dark energy that's accelerating the expansion of the universe. One single tool describes it all. It's incredible.
And so, here it is, the grand finale. We take our perfect cosmic recipe, the stress-energy tensor T alpha beta, and we put it on the right-hand side of the equation where that placeholder used to be. And we finally have it, the complete Einstein field equation. This is one of the most profound statements in all of science. On the left, pure geometry. On the right, all the stuff and energy in the universe. And the equal sign is the link. This is how the universe works.
So we found our answer, but of course, every great answer just leads to an even bigger question. We live in a universe that's constantly expanding and evolving. The matter spreads out, the radiation cools down, which means the stress-energy tensor of the entire universe is changing over billions of years. So the question I'll leave you with is this. How has this evolving cosmic recipe shaped the entire 13.8 billion year story of our universe? And what does it tell us about where we're headed?